Go ahead and push record. I'm just waiting for Elena to say we're live. Hello, everybody, and welcome to day 2 of the 225th meeting of the American Astronomical Society. My name's Tony Darnell. I work at the Space Telescope Science Institute. And one of my favorite things about coming to this meeting is I get all the latest updates of everything that's happening. And with me is my good friend Alberto Conti. Hello, Alberto.
Hi, Tony. How are you? Good to see you again.
So today we're going to pass the mic around back and forth, and we are going to get an update on the James Webb Space Telescope mission. And we've got with us today Scott Willoughby. He's the mission you're the project manager, right? Yeah, for Northrup Grumman, and as well as John Ehrenberg. He's a chief engineer for the mission. And so no two better people qualified to give us an update than these guys. So I'm excited to hear what they have to say. But before we get started, I want to tell you that if you've got questions for these guys or comments you want to make, you can do it on YouTube, where this is being broadcast as a live event on the NASA Webb Telescope channel. You can also interact with us on Twitter using the Hubble Hangout hashtag. I know this is a JWST thing, and we're working out the branding on this stuff, but we're looking at Hubble Hangout, as well as the G+ page, the event from which we created this. So we hope you'll leave us comments and questions. We look forward to getting to them, and I have my good friend Ishan Prescott from Goddard monitoring you, and he will let me know when you guys do that. So let's get started. Scott, it's been a year since we've talked last. You gave us a great update on the mission as of last year. You also gave us a good explanation of how these parts are built, being space qualified, and got a lot of great response from that last year. So what's happened since we last spoke?
It's been an incredible year in the telescope. I always feel that it's helpful before I give status on it just to explain how we build this telescope, just to start off. And it's cool having the picture for us behind here. But when we build a telescope, it isn't just one big thing that's coming together all at the same time. It really happens in 4 sections. The optics that you see, the real shiny part there, the mirrors get put together in a composite structure called a backplane. The Sunshield, the big deployable thing that's going to keep those optics cold, minus 400 degrees Fahrenheit in order to do this infrared mission, it gets put together as an element. The bus, which every spacecraft has to, point it on orbit, transmit data back and forth, receive commands, send telemetry, gets built together. And then behind the optics and the backplane is what's called the instrument, the science model, integrated science instrument module, where the 4 key instruments are coming together. So those 4 elements have made an incredible amount of progress throughout the year. It's happening around the country. Everything's being kind of collected now, either mostly between Northrop Grumman and Redondo Beach, or NASA at Goddard Space Flight Center in Maryland. Just to kind of hit each of those areas, kind of quickly. The 4 instruments have now gone through a second cryo test at Goddard, which was very successful. So they were subjected to their on-orbit temperature environments.
These were the ones in the ISM you're talking about?
Exactly. In the ISM, so the NIRCam, the NIR spec, the FGS/NIRIS instrument, and the MIRI instruments all got tested together on their optical platform in true on-orbit temperatures. And we're very successful at testing those. The optics are actually complete, the flight mirrors, but what we're doing now is we're doing a trailblazer activity where we've actually installed 2 flight-like optics into a trailblazer backplane, which is done with a robotic arm that Excelis, built for us with the software to actually precisely locate mirrors within a backplane. Super cool, and you can go on the webcam through the NASA site, and I think every 60 seconds they update a photo of the high bay, and you can see a Pathfinder with 2 primary mirrors and a secondary mirror. So we're proving out the techniques to install mirrors, and in 2015 we start the installation. Actually, we'll finish between the summer and the winter installing all 18 primary mirror segments into the flight backplane. So
that'll be impressive to see.
It's going to be an awesome milestone. You're going to have that big shiny 18 gold mirror segment.
It will be a webcam, so you can actually you can stock it. You can actually look at it, which is great actually.
So that's 15. And then the big thing we did this summer was on that Sunshield, we built a full-scale development model. So 5 layers of a Sunshield in a structure, and we deployed it. First time we've ever deployed a 5-layer Sunshield, both, long, wide, and then separate the 5 membranes. And we proved the deployment techniques and the dimensionality of that separation of the membranes.
And that test is just going to be one of many, right? I mean, I'm watching it playing out on the model over here. Yeah, and this video is available also online as well. But you're going to be tilting it in different directions and doing the same kind of test too, right?
So we do 2 big deployments with what we call our engineering model. Full scale, flight-like membranes, built exactly like they would for flight, with just maybe some different coatings because it's unimportant for the deployment test. We're doing a second one of those, come about probably spring, summer of 2015, with more upgraded hardware to make it more flight-like in the rim and the hub. And then we do it 3 more times on flight, because basically you need to deploy it when you install it to make sure that it's worked and it was installed properly. You need to deploy it very flight-like when you're in what's called pre-environmental test, before you simulate the rocket launch, before you're going to shake it like it would on a rocket. You want to prove, what it looks like in that condition, and you stow it. Then you shake it just like it would on a rocket, actually a little rougher, right, to prove you have margin. And then after that, we'll deploy it again to prove that it deploys successfully, nothing binds, that it comes out to the same dimensions it wants. So we got 4 more, 1 on a test model, and then 3 more on flight.
Wow, so that'll be amazing to see that come about. John, let me ask you, how scary is that? These deployments, are they nerve-wracking to you? Because when we all look at them, we get a little bit worried that it might get stuck or something. How scary is this to you guys?
I think the real nerve-wracking part is leading up to the test. A huge number of man-hours go into the planning of the test, and everybody hopes that the test is anticlimactic. But of course, it's very emotional when it actually works. The amazing thing about our test this summer is it worked almost 100% flawlessly. There were some very minor glitches that looked to be just an artifact of the ground test. And so it really validates the man-years of work that the Sunshield team put in to get ready for it. So the exciting part is watching it happen. To be honest, the nerve-wracking part is the 2 years leading up to that one singular event.
So, I can imagine. So, Scott, is everything looking pretty good? Are we still on track?
Yeah, our progress has been tremendous. We continue every year to go to Congress and ask for the same budget we said that we would ask for in 2011. Our replan look forward all the way until the 2018 launch. And we've continued through, now we're into fiscal 15, running at that same rate. And then at the beginning of every year, we declare a number of significant milestones. The big things like deploying Sunshield or delivering major subsystems or components, or integrating and testing them. And we make most of those on time or ahead of schedule, and the few that have been missed within that usually get replanned with something else comes in sooner, something goes later. So there's been no impact on our October 2018 launch date or on our fiscal cap. So we're performing very well. Great.
So are there any other updates you want to let us know about?
We continue to learn things in the development, which is great. I always like to people hear the great story, which we want to tell. It doesn't come without, like John said, the trials and tribulations. We've done a great job. If people were following things along in other press and stuff, a couple of years ago we were working through mass issues as we were making sure we could fit in the capacity. That is well behind us. Excellent mass margin now to the rocket launch, so that's really good. And we're building that flight hardware, and we're measuring it as it comes off of the production lines, and it's right within what we predicted it to be. So real good progress there. We're building the structure that's going to hold the Sunshield and protect it for launch. Earlier in the year, in our first base article, we had a development in the manufacturing issue. We've now since corrected that. We've built the first side, which is called the aft. It comes in a clamshell. And just before the Christmas break, we finished the forward one, and now we're going to send that into a test. But we completed the manufacturing, so that clamshell is now built for the Sunshield. So we continue to make progress on the path that we had predicted, where we put in time to learn things in the development phase, and then when we get into the production phase, we're hitting our mark.
Okay, well, in a minute I'm going to ask you about what's coming up for 2015, but I want to ask about the rocket for a minute. This is being built by the French, correct? This is a French rocket?
European Space Agency, of which the French play a large role, so yeah, certainly it's a
Ariane 5.
Yeah, it's the Ariane 5. It does launch from French Guiana, and Ariane Space, I think, is headquartered in France, but it's a number of partner countries that are a part of it. So we're going to launch on the Ariane rocket, which again will launch out of French Guiana in 2018 to take us at 1 million miles away, 1.5 million kilometers away from Earth to the L2 point.
Yeah, I'm going to get to that too in just a second as well. But does the rocket have to be modified in any way? I mean, do they have to do anything special, or is it like an off-the-shelf, like buying a Boeing or something? You get a standard rocket, and then you just put your stuff in it.
I mean, this is the space business. There's no such thing as off the shelf. So every payload is accommodated for its mission. But we're pretty much within the standard normal processing of a payload. And the Europeans have put the Herschel and Planck and the Gaia mission at L2. So there is history within this very highly reliable launcher of putting large things in L2.
Yeah, and the reason I'm kind of talking about the rocket right now is this is one thing we don't really touch on, and I'd like to start getting people thinking about this a little bit. I had heard, first of all, that we're taking it down there via a barge or something like that, right?
Yeah.
Which is amazing in itself. But they had to make accommodations at the launch site for the weight of the rocket, or what is that?
So what happened earlier on in the program, it was going to be a flight transport, right. But where you land, what's called the skid strip or the airport, on there, between there and the launch processing are a series of bridges to go over whatever canals, rivers, waterways in there. Most of the missions that launch on the Ariane rocket tend to be tandem ComSats to geosynchronous orbit, so they can kind of come in one at a time. Webb is one large mission where 6,500 kilograms of mass as just the article itself, not to mention all the instrumentation and things to keep it clean and in a controlled environment, in the shipping container and what it takes. So it's a very large convoy, and that would have been in excess of the capacity of the bridges. So what they came up with was a solution to actually take the same barge that takes the boosters from Germany to French Guiana, coming across the Atlantic, bring that into the port of Los Angeles. We'll load on that. We'll go through the Panama Canal. We'll come around to French Guiana. And if you load from the beach side, you can come on land without going over a bridge into the processing facility. So we solved that problem.
And one thing I can imagine is everybody's going to be looking at the weather reports quite closely during that trip too, right?
No, but it's interesting. There are contingencies of what happens if you have bad weather on the way, right? They need to be able to, of course, because you don't want to get stuck in the middle of any ocean, right?
Yeah, that'll be a tense time. That'll be a lot of tense moments. But John, let me ask you, as a chief engineer on the project, how are you? Are you satisfied with the progress? Are things going as you had hoped?
Yes, I'm thrilled with the progress. The team is identifying challenges, knocking them down as quickly as we can find them, being very comprehensive. The thing that most worries me is missing a problem and not discovering it until late. Maybe even after launch when we don't have the ability to affect it. So we're really comprehensively reviewing the design, the performance, the test results, asking ourselves the question, did we ask the right question? Is this system going to perform as we expect? And we're making great progress in that area in all fronts, from mechanical, electrical, thermal design, everything.
So help me understand the workflow a little bit. Northrop Grumman is building certain components, as I understand it. Ball Aerospace is building other components. Different people have different things. It's all getting assembled, though, at Goddard. Am I right?
So it gets assembled in multiple places as it comes into its bigger structure of the force. So you're right. The major subcontractors have done the lion's share of the work in terms of Ball Aerospace is responsible for the optics and also system engineering associated. But think of hard deliverables, the shiny optics, which are complete. And ATK out of Magna, Utah, built the composite structure that's going to hold those. And that composite structure has been delivered to Northrop. So we built it up with hinges and mechanisms. So those two are there, and then I mentioned Excelis, does the robotic arm for us that's going to install the mirrors. They also do the metrology, the test equipment for the Johnson test. But the way it comes together kind of is almost three paths or two paths that come together ultimately at Northrop Grumman is where the final build of the telescope, or what we'll call the observatory, will be. Goddard has the instruments, and then we will install the mirrors in the backplane at Goddard, and then the instruments will get installed into the back of that. Okay. When that's complete, it actually then goes to the Johnson Space Center for cryogenic testing of the integrated optics food chain with the instruments to prove that you can actually measure through, focused light, from optics into a focal plane of the instruments. That will happen at the Johnson in what they call Chamber A, which tested Apollo back in the 60s.
That's right. So I'm going to have John describe that for us. What is that chamber at Johnson that's going to be used?
So the Chamber A is this huge vacuum chamber about 9 stories high.
And it's a national historical site or something.
It's a national historical site. The agency got it historic site designation to save it from being scrapped, and then it actually complicated the remodeling, believe it or not. But this is
because they didn't want anything changed because it was a historical museum piece.
That's great, and that's part of what goes into being a historical designation. The chamber itself has a 55-foot door, which when we go through into the door, we clear by 6 inches on the top and 3 inches on the side. So, big telescope, big chamber. It will get all the way down to flight temperatures, and it has a complete suite of optical instruments to measure the performance of the telescope and convince us that we have built the right primary and put it in the right place to enable the mission.
Now, when you say it's sort of a tight fit, is that with the heat shield not a part of it, or is it fully deployed? Or
no, the Sunshield is not included. So this is just basically what we call the Otis, which is a portmanteau of OTE, that's the OT, and the Integrated Science Instrument Module, the IS. So if you want to think of that as the optical payload section, that's what goes in there. There are thermal simulators for the spacecraft and bits of the Sunshield where they're relevant to getting the right performance of the Otis. But the full-scale Sunshield will be in full tilt construction along with the spacecraft at our facility.
That parallel path I was talking about. So the optics and the instruments get integrated in Goddard, get tested at Johnson, and they deliver to the Northrop facility in Redondo Beach. At the same time that's working, we're building the Sunshield, the flight Sunshield up, and the bus, and then they get integrated as an assembly, and they get tested, and then those two halves come together.
Okay, yeah, sorry. I'm just looking at Ishan. My computer crashed or something, I guess. So I don't know if I'll be able to get the comments. Yeah, really. Yeah, really. So, Alberto, let's take a step back for just.
You saying "oh no" when we talk about the telescope.
Oh, yeah. Talking about my computer.
I want to minimize that.
Yeah, my computer. We'll say that all the time about my computer. So, Alberto, let me ask you, let's step back just a little bit and give us a brief overview of some of the science that people are that we're hoping to be able to do with JWST, how it's an improvement over Hubble, and some of those kind of questions.
So the first thing we have to say is it's an infrared telescope, so it's very different from Hubble. So it looks in the infrared for specific reasons, right? So there are 4 specific reasons why it does that. It's an infrared because we want to basically at first look at the first remnants of supernova that exploded, 30.6 or so billion years ago, right? So those are the first stars that were ever formed in the universe. They were very, very different than the stars that are formed today because they were now rich with metals, with material. We call them metals in astronomy, which is a misnomer, but things are heavier than helium and hydrogen. So these stars are very different. They're going to be extremely large. They're going to be live very shortly and explode very powerfully. And so we hope to actually look at the light because we can understand the conditions in which they form, right? And so together with that, we also are going to look at the first galaxies because we have the resolution to see those first galaxies in infrared. But then, for it's either sheer luck or brilliance on our part, the universe works out in such a way that if you use infrared, you can actually penetrate clouds of dust. And so when you do that, you actually look at inside the star formation region where you can actually see stars being formed, which is something extremely interesting because if you're here, probably even today, we are bombarded with posters about exoplanets. And so that's what forms around stars typically, planets like our own. And so Webb will be the first telescope in history that will be able to actually look at those planets around stars and ask, do we have water in some of those, And so this is a tremendous, facilities that we have that will actually be able to first ask those questions, and then, I think our appetite for the next missions that will actually characterize those exoplanets, right?
So I think we're gonna. I was at a session last night, UVORI. Future of Astronomy and the big space telescope. So I think we've got a hangout coming up on that later in the week, where we're going to talk about what's possible after James Webb. And so the ability, I think. Do you think the telescope will be able to answer the question of, are there habitable worlds out there? Are there worlds with Earth-like worlds with water on them, or are we just going to look at exoplanets and sort of get a statistical model of where they all are?
Well, I mean, that's a very interesting question. I think so. I have a two-part answer for that. So the first is that, if you look at what Webb can do right now, a face value, right? Not knowing what you will find, which is a big unknown. I think if you look at Hubble was built for doing something, and he found 150 other things that we didn't know, right? So the hope is that. So if you look at face value, I think we're going to be very good at characterizing Jupiter-sized or maybe Saturn-sized objects, and maybe finding in the atmosphere if they have water. If you're very lucky, we can go even smaller. But the problem is that Webb cannot look directly at these planets because the stars are too bright. So you have to basically do a subtraction. You have to look at the star when the star is with the planet and without the planet, and then you analyze the light from the planet's atmosphere. So if the planet is too faint, then we're not going to be able to find it. And so faint means small. On the other hand, I'm a kind of optimist in the sense that there might be a lot of things that we don't know, and we might be very, very lucky. Maybe in the solar neighborhood, we're going to be able to find traces of water in planets that are much smaller than what we think the Webb can resolve, right? And so, I'm optimist because I've seen the history of 25 years of Hubble, right? And so I think that's I'm going to withhold judgment, until we launch in 2018. But I think we're going to be very surprised about all the things that we find.
So, John, I have a question for you, which is this month we've kicked off our anniversary of 25 years of Hubble in being in orbit and giving us great discoveries and things like that. What are you doing to design? Okay. I'm getting prompted to. We lost our connection to my computer. So if you guys will go to Twitter and tweet your comments and questions using Hubble Hangout or the JWST hashtags, we'll be monitoring those. Unfortunately, my computer went down. So please tweet any questions or comments. I'm sorry about the technical difficulties, but this is what live is all about. So thank you for doing that. We'll look for your comments and questions there. So Hubble's been up there for 25 years. We're designing James Webb Space Telescope for presumably a certain amount of time. What are the design specs for that?
We have a requirement to operate for 5 years after our 6-month commissioning. We very carefully monitor our consumables, which are mainly fuel, and they're budgeted in an extremely conservative manner so that consistent with other spacecraft we've flown. Chandra had a very similar requirement. It's on 15 years. It may go as long as 25 or 30. We have also built the first man-made objects to leave the solar system earlier in the company's history. So our design philosophy is to use a very robust design approach and conservative analysis so that we are clearly able to meet our requirements. And to do that with high confidence, we usually wind up with much longer-lived performance. Chandra being the most recent example.
25 years. God, wouldn't that be great? I mean, that would be amazing. I mean, anything. So you're saying, so there are consumables. Obviously, it can't be repaired because one of the reasons the rocket that is being used is so big is it's got to go and push the telescope 1 million miles away. It's going to a special point in space. Can you tell us a little bit about that?
Sure. It's one of 5 so-called Lagrange points. These are points that orbit synchronously with the Earth. That is, they complete their path around the Sun in 1 year, and the Earth maintains its same relative position.
It kind of follows the Earth as it goes around the Sun.
Yes. So the L2 is 1 million miles away from the Sun, and we are actually orbiting. From the Earth. Thank you. It's also more than 1 million miles away from the Sun. It's about 94. Thank you. And we're actually orbiting in a large ellipse around that L2 point. This enables us to do a couple of very important things. Number one, we're away from the Earth, which limits our view to the whole sky and also presents a huge thermal input. One of the key things that we need to do to detect the faint objects that Alberto so eloquently described is we need to have the telescope stable and able to point for long periods of time, days, weeks. We have a requirement to be able to take an image for up to 10 days. So we want the telescope to be
Pointing in one spot for 10 days?
up to 10 days without having to repoint. This requires tremendous stability on the level of nanometers over that period of time. So the way we do that is we have materials that change very little with temperature, and then we try not to change the temperature. So one of the ways you do that is keep the solar input constant. By going to the L2 orbit, we can be outside of the solar. We have constant solar input and have no shadows from the Earth or the Moon, which, number one, means we're always in sunlight. The solar array is always on. We don't have to take a big battery. In fact, we have a very small, tiny battery, probably smaller than one in your car by mass, and it's only there for when we come off house power in French Guiana to when we get the solar array out 32 minutes after launch. That's all it's there for. That's all it does. It obviously plays a role in the electrical power system, but we're never on the battery after that. The bottom of the Sunshield is never in shadow, ever. And this combination of effects enables us to build the system that is JWST. So the orbit is actually an integral part of the design.
So, and you mentioned this constant solar input. I don't know if torque is the right word, but there's some kind of force on the telescope that
yes.
you've compensated for.
Yes.
Using something called a momentum flap, I believe, right?
So light photons have no mass, but they do have momentum. Yep. It's the back part of the Sunshield there, and that's a really great engineering story in and of itself. A few years ago, when we were finishing the design of the Sunshield and had to commit to the shape and the construction, we did not know the mass properties of the flight satellite. And if the center of pressure, that is the center of where the light, the projected area that is illuminated by the sun, is offset from this balance point, you develop a torque. Essentially, the Sunshield is like a solar sail and wants to overturn the satellite. We compensate for that with reaction wheels, but eventually we have to desaturate the reaction wheels using propellant, our one consumable. So we added the momentum flap, which allows us very late in the game. It's practically the last thing we do before we get on the boat. After we take our mass properties, we set the angle to do the best job of balancing the area forward and back of that balance point. This allows us to minimize propellant usage over lifetime.
And hopefully increase the mission life as well.
Increase the mission lifetime, because we have done many studies that shows that the mass of that momentum flap pays for itself many times over in propellant. So it's a good example of engineering design serving the ultimate mission function.
That's amazing. That's really cool. It's one of my favorite things to talk about, too, because I think it's such a cool story as well. So I'm going to ask you this. We all know that L2 has a lot of special properties as far as its orbital characteristics. We put a lot of telescopes there, and a lot more are going to be going there in the future. I think WFIRST is going there, isn't it? Well, I don't know yet. Yeah, I guess we don't know yet. But anyway, it's a very popular place in space, and as you mentioned, it's got a constant solar input to the telescope. It's gravitationally stable. You said more? No,
it's not. Oh. It is unstable. So we must actively maintain our orbit
with the momentum wheels and stuff.
We have two station keeping maneuvers. So if when you're viewing the orbit from the Earth, it looks like a huge oval, 500,000 by 800,000 kilometers thereabouts. Okay. And we have to perform a station-keeping maneuver essentially at the top and the bottom of each one of those ellipses, roughly every 6 months. If we don't do that, eventually we will drift away. This is an unstable. There's only two of the 5 Lagrange points are stable. The ones L4 and L5, famously known for the Trojan asteroids in the Jovian orbit, which is how they were discovered. So we don't have a stable area.
But one of the things, and I think I remember this from past conversations with you, and I want to ask the question because you get it a lot, we get it a lot, is how worried are you about little small meteorites hitting it or getting punctures in the Sunshield, things like that? How worried about you are those? I'll
give you the quick glib answer. I'm not worried about it. We are going to get hit. It's just That is the environment. It is one of the environments that we have designed the satellite, the system for. So we have done testing, hypervelocity testing on the major components, the Sunshield, the mirrors, and we understand their effects and have included the effects of the predicted natural environment on the system. That's part of what goes into the lifetime prediction, right? I have to be able to give my boss, Scott, the nod that our design will meet requirements. This goes into our calculations of probability of mission success at 5 years.
So this will sort of, I mean, obviously these hits would degrade it over time. The primary, if it gets hit a lot, might sort of degrade over time as well. But you've planned for all that.
So in what we call the error budget or the performance budget, we're allowed so much imperfection, right? Engineering is the art of building a system with imperfect parts. And so the trick is how imperfect can they be? And so we allocate in a budget form a certain amount of imperfection or lack of performance to each of the factors that affect our design. So in fact, the mirror budget does have a small allocation for increase in wavefront due to micrometeoroid strikes. The optical properties of the Sunshield, I know this because I just recalculated it right before the break, does explicitly include the effects of micrometeoroids. There are other environmental effects in all of those budgets, but micrometeoroids are explicitly included. So my first order answer to you is I'm not worried about it. It's included in the design.
Okay, so the mirrors are made of gold. You look at it, but they're not made of gold. Let me correct myself. They're not made of gold. Yes, they're coated in gold. They are coated, right. They are made of what?
Beryllium. Yeah, so the mirrors, the structure of the mirrors and the polished form that meets the requirements of being able to point this accurately is a beryllium powder. I mean, literally mine beryllium powder, forge into a block, machine down, something on the order of 90+% of the forging gets machined away or polished away, resulting in actually a very thin face sheet with a kind of what's called a ribbed structure behind it to give it, the stiffness. Those are made out of beryllium because at their operating temperatures, 38 degrees Kelvin, somewhere in that ballpark, they're very stable. Even with that stability, though, there are 7 actuators on the back of every mirror, one for each of the corners and a center of curvature one. So there is some commandability on orbit to make adjustments, say for thermal conditions or something that happened dynamically, during the launch in terms of where their placements are within the backplane. So they can be correctable and reconfigured with what's called our wavefront sensing and control software. But they're a beryllium base with a thin layer of gold to reflect infrared.
Well, that was where I was going. I'm meaning to say there's a very thin layer of gold on top. And you said two grams, you said?
Yeah, it's 50 grams over the whole primary mirror.
I think the thickness on the surface is on the order of angstroms.
So you don't need much to reflect the infrared. So
Yeah, you have to remember, you have these photons that have been traveling for 13.6 billion years. They're very tired, right? You want to make sure that you don't, absorb anything. You want to reflect as much as possible. They're very, very precious photons, right?
Well, that's where I was going with the whole gold comment, was that we want this because
gold, not just to look cool and shiny, but it is a nice after effect that makes it look great. But
it's nice. It is nice. So let's get to Scott the future. What's next up in 2015 for you guys?
Yeah, so we're at the stage when we kind of would have talked at the beginning of last year, manufacturing would have been a big part of building the subcomponents, so to speak, that go into it. We still will complete that out. So like Sunshield flight layers, now that we've demonstrated with the engineering model layers that they meet their requirements in a deployed state, they're being built. They kind of finish in early 16, so a heavy year to produce and finalize the Sunshield membranes. At the same time, though, most of its structure will actually be built. I mentioned the clamshells, the telescoping tubes that pull it out on the width side, those will be built. The backplane will get delivered to Goddard, the backplane that holds the mirrors, and will actually robotically install the mirrors, and that is scheduled to complete by the end of 2015, 18 mirror segments in the backplane. So that
You want to come and see that? I mean,
that's going to be a remarkable accomplishment in the optics. And then in the summer of next year, the last crowd test of the instruments as just an instrument package. So the 4 instruments get their final test and verification. That occurs in the summer of next year. It's crowd test number 3. And then when that's done, now I got mirrors and a backplane, and I got the final tested instruments in their package. They go together to deliver to Johnson for 16. But in 15, you'll get that last crowd test, and you get mirrors installed in the backplane. You'll have almost all of the flight Sunshield parts completed, and our bus will be near complete in terms of delivering the avionics boxes and the power subsystem boxes, getting ready to deliver those into INT to start putting on the actual bus structure in 16. So
now we're just building. We're
building and
putting
testing.
All right.
I think we have
I was going to say, while you read that, I was going to say that it is a palpable excitement in things that you see at the Space Park. So.
I mean, the key thing is each of these these phases, which is kind of a build, test, build, test, build, test. That was a significant part of the planning that we did in 2011 for a complicated system like this, is to make sure we are learning. Like John said, we want to learn lessons as soon as possible. So you have the runway there. All of the things that we're doing now are being done on that schedule that we declared in 2011. So we are in 2015. We're about halfway through, call it, that last part, that replan, where we had just come out of the mission CDR, right, and then a launch window in front of us. So we're halfway through that now. Design's complete, manufacturing of parts complete. Now parts coming together and then going through their tests before they come with the next set of big block of parts to come there and get tested. And that's running on schedule. And this is a year where more big things come together.
Yeah, I'm excited to see it. And it's amazing we have to remember that in the early parts of the design of James Webb, stuff didn't exist. Things had to be invented, to make this telescope happen. And now that we've done that basically, I don't know what. To me, that seems like the hardest part. The hard stuff has been done. The hard stuff's been answered. Now we're building. We're just building stuff, and then we're putting it together when we're implementing it.
To borrow a quote from elsewhere, the only easy day on JWST was yesterday.
Fair enough.
The program did make a huge commitment, and the agency drove it to do the technology development very early. In fact, it was part of the program confirmation. My first job was, in fact, running one of those technology development tests. And it's what enables this amazing technology. I'll put a few locker room numbers together. Hubble has roughly 1/7 the collecting area of JWST, but weighs 11.1 metric tons. We weigh 6.5 metric tons with 7 times the area. That's roughly 15 times more efficient at the system level. When you look at it at the primary mirror level, it's, I believe, even more efficient. That was enabled because we took a very different approach to getting the stiffness necessary to make the mirror. The mirror as a system, the primary mirror as a system, where the light meets the mirror is, of course, in that first 1,000 angstroms of gold. But to get that exquisitely coated surface in the right place, it requires the mirror substrates, the motors, and the backplane to work together essentially as a symphony. All of that had to be designed, developed. We had to convince ourselves it was going to work. We had to convince non-advocates that it would work. And more importantly, that we knew how it was going to work at the nanometer level. So it was tremendously challenging and enabled us to do I'll call it the workaday engineering that we had to do, fight the mass problems, fight the thermal design issues, and all of the other things that has led us up to this point. So, we have to kind of be humble and a little bit scared and run hard. So it'll be easy after we turn over the keys of the commissioned observatory.
Yeah, it's easy for me to say. It's easier for me to say stuff like that because I'm not working. But I can imagine that there's still, every day is still a big challenge. And so, well, this has been great. Has there been anything on Twitter? Did we get anything? Okay, I'm sorry about the comment glitches, folks. We hope we're still working out some of our own bugs here as well. So on the Hangout technology. So I want to thank Scott Willoughby. Thank you very much for joining us, and John Ehrenberg. Thank you very much for joining me. It's been wonderful. Next year we're going to meet again.
Absolutely.
All right, we got to keep doing this. Yeah, Alberto.
Before then.
Yeah. Okay. Good. I hope so. You have any comments?
No, I just want to say that, I don't have a Scott job. He has a lot of people working for him in Northrup Grumman. I would describe the excitement that I see every day when I go in the clean rooms and see how they work as palpable excitement. There are people like John and people that work all for Scott that are incredible professionals. They are excited until the last minute for the test, and then it's beautiful to see this test going so well. But there are a few things that keep you up at night, perhaps, Scott. There are a few things that you have to still address. But it's beautiful to see how all of this is coming together. It's actually fantastic. So next time I'm going to invite you to come to Space Park and actually see how we build this.
Do one in front of the window of the high bay.
Absolutely, we can actually do an hangout like this in front with the backplane behind us, for example. It'd be fantastic.
Great, that sounds great. So subscribe to the NASA Webb Telescope YouTube channel. Also follow us on NASA Webb Telescope and on Twitter. And all of that will be announced, and as soon as we work it out, we'll do it again. So thank you all. This has been great. Thanks. I love hearing about JWST. Can't wait for 2018. Thank you guys for watching. And that's it for right now. We'll have another hangout at 3:30 Pacific time where we will be looking at the most highest resolution image of the Andromeda Galaxy ever taken. It was taken by the Hubble Space Telescope, and it was released yesterday, and we're going to talk with the people who made it. So that'll be at 3:30 Pacific. So we hope you guys will tune in there. Thank you all for watching, and as always,